So, you start from your energy balance. Q plus the shaft work minus change in enthalpy minus change in potential energy minus change in kinetic energy. So you know it's the process is adiabatic. You assume it's adiabatic, no heat transfer. So that's you set that 0. No thermodynamic state change, nothing's changing, no gases, whatever. So that's set to 0. Assume kinetic energy equals 0, as always. So the change in the shaft work in this case is only the change in potential energy, because it's just something falling. It's just water falling. And what's potential energy? Mg delta Z or mgh, change in height. The change in height is negative 2.5 meters, because it's falling from a height to a lower height. And your answer is 9.81 kilowatts. All good? If the energy is used to heat water from a shower, calculate the maximum flow rate of warm water when the cold water inlet temperature to the shower is 10 degrees and the shower outlet is 42 degrees. I'll go through this one. So, shaft work equals the change in enthalpy, and the mass flow rate times the change in equals the change equals the mass flow rate multiplied by the molar change in enthalpy. Now that gives you mass flow rate equals shaft work over the change in enthalpy, and from the steam tables you can find the enthalpy of water at 10 degrees, 41.96 kilojoules per kilogram. Enthalpy of water at 42 degrees equals 171.82 kilojoules per kilogram, and the enthalpy, the total enthalpy change equals 171.82 kilojoules per kilogram minus 41.96 equals 129.86. Something similar to this will be in topic 6, which almost always turns up in the exam. So learn how these enthalpy changes work. The mass flow rate is 9.81 over 129.6 kilojoules per kilogram, which gives you 0.076 kilograms per second, equals 4.5 per minute. It's just a unit, kilograms per minute, 1 kilogram. Yeah. This is the amount of the flow rate you require to heat up that water to 42 degrees from 10 degrees. You know, potential energy can convert potential energy into heat, because energy cannot be created or destroyed. Remember, Captain Schultz diving from that height into a bath to increase the temperature. Exactly the same. A flow of 1,000 meters cubed per minute of carbon dioxide with a Cp equals 55 joules per mole per Kelvin at 1,500 degrees and 1 atmosphere is cooled in a long tube heat exchanger to 700 degrees by cold water, which is heated in the process from 8 degrees to 68 degrees. Estimate the cooling power needed to cool the carbon dioxide gas. So you have your heat exchanger. You're doing heat exchanger designs anyway, so this is you've probably seen this before. So the change in heat equals the change in enthalpy, which equals molar flow rate with respect to the change in multiplied by Cp with respect to change in temperature between the two temperatures. So NCP T2 minus T1 equals NCP delta T. And you calculate N from the volumetric flow rate over the molar volume times Cp delta T, and the molar volume heat with respect to heat capacity and temperature is independent. These are all heat capacity is temperature independent, ideal gas. So PV equals nRT, and the Vm equals 1 mole multiplied by RT over P equals 1 mole times 8.314 R times 1173 your temperature over 100 kilopascals times 1000, which equates to 0.147 meters cubed per mole. Hence, the heat flow equals volumetric flow over Vm multiplied by Cp delta T, and your answer will be 108 kilojoules per second, which is 108 kilowatts. That's how much power you'll require. So, determine the coolant flow rate. That shouldn't be A, that should be B. Q equals MC delta T, or as I call it, Cm delta T because it's easier. The mass flow rate equals Q over Cp delta T. You can calculate the mass flow rate. Yeah, you've seen this, you've done this already, I think. Yes, heat exchanges. So I'm not going to go too much details. You guys have not seen it, but you'll need them in process design. It's in Colson-Richardson anyway. Consider an adiabatic turbine. I'm just trying to get through this quickly so you get the answers as well. That is fed with water at 1,000 kilograms per second, 10 bar and 8 degrees. The water leaves the turbine at 1 bar and 8 degrees. Assuming that water is incompressible, that kinetic and height effects are negligible, and taking the water density to be 1,000 kilograms per meter cubed, calculate the power output of the turbine. Again, it's potential energy related. So, from the first law, we know shaft work minus delta H equals 0. Shaft work equals delta H, which equals delta U plus change in change in pressure multiplied by volumetric flow rate. Hence, we can the change in internal energy for the flow rate equals N multiplied by the integral of Cv dt, and T2 equals T1. So change in pressure multiplied by volume equals PdV. Basically equation plus a change in pressure with respect to volumetric flow rate, and the shaft work equals the change in volumetric the change in volumetric flow rate with respect to change in pressure. So your shaft work equals volumetric flow rate multiplied by the change in pressure equals the volumetric flow rate and your change, your volumetric flow rate is your mass flow rate over density, so the amount of mass you have and the density, so that's your volumetric flow rate. Multiplied by pressure, so you have the mass, you have density, you can calculate the shaft work, which equals negative 0.9 megawatts. Try to do these and let me know if the answers are wrong. It could be wrong. But only numerically, not algebra. Hopefully. So, last question, so you can go home. An adiabatic flow nozzle is an ingenious device that transforms a slow flow of hot gas into a fast flow of cold gas. I'm not sure what's ingenious about that, but in the present case air, molar mass equals 28.9644 grams per mole at 600 Kelvin, and negligible velocity enters the nozzle and leaves it at 500 Kelvin. Determine the velocity of the gas exiting the nozzle, given that the air may be treated as an ideal gas. Cp equals 7 over 2R because air is, we are assuming air is diatomic. In this problem, we use the fact that for an ideal gas, the internal energy and the enthalpy depends on the temperature only and are independent of pressure. So, change in kinetic energy equals the negative change in enthalpy, because there's only movement, there's no potential energy. Yeah, working from first principles, and change the mass flow rate over 2 times the change in velocity equals negative n change in enthalpy. That's your enthalpy change, and your Vn equals 0. So n, the molar flow rate multiplied by the mass of the air over 2 times V V out equals n negative molar flow rate times change in enthalpy. Hence, V2 out equals 2 change in enthalpy over m equals negative 2 Cp delta T. Remember, change Cp delta T equals change in enthalpy, and you see it on the other side. V out equals 448.25 meters per second to meet the above criteria. Final slide, and I'll do